Namaskar. Today we have come up with another video lecture in which we'll be dealing with another part of reversible inhibition of enzymes. We had already discussed that reversible inhibition of enzymes are of three types. They are competitive, uncompetitive and mixed. And in mixed type, we had discussed in the previous lecture, the mixed type, a special case is called non-competitive inhibition. So today, basically, we'll be dealing with uncompetitive inhibition. Uncompetitive inhibition. Today, we'll be dealing, first we have dealt with competitive inhibition, already done. Today, number 2 is uncompetitive inhibition. Our main focus of the lecture would be uncompetitive inhibition, and another one is mixed inhibition or mixed inhibition. A special case of mixed inhibition is non-competitive inhibition. So let us start with uncompetitive inhibition. Let us start with uncompetitive inhibition. So first one we have already dealt, competitive. This is already completed. So today we are not going to discuss competitive inhibition. Competitive inhibition we already know, and we had already drawn the graph in our previous lecture. So this one is already done. Today we are going to start with second one. Okay. So let us come to the point. Uncompetitive inhibition. In case of uncompetitive inhibition, a very important thing to notice here is that the enzyme reacts with substrate, you already know, to form enzyme substrate complex, and then enzyme substrate complex converts it back into enzyme and product. Right? The uncompetitive inhibitors does not bind to the enzyme. It binds to the enzyme substrate complex. This is very important. The uncompetitive inhibitor binds to the enzyme substrate complex, and that too distinct from the site of the substrate. That means they don't bind to the active site. They bind to some other sites other than active site and to the enzyme substrate complex. Means after the substrate has bound, then to the enzyme substrate complex inhibitors bind and form enzyme substrate inhibitor complex. So if suppose this is the enzyme and we have two sites, say one is like this and another site is, say it is like this, then you will see the substrate, say substrate is coming and binding, this is substrate, then substrate is coming and binding to the, say, okay, so let's say substrate is coming and binding, okay, and then here also we have, let us say like this and this way. Then here substrate will go and bind first. Substrate, this is substrate. So the substrate is coming and binding here. And the inhibitor, once the substrate has bound, then the inhibitor, the substrate, then the inhibitor, say inhibitor is, say this one. This is the inhibitor. Say this one has blue color. So inhibitor will come and bind here. Can you see there? So what do you see? The inhibitor, this is inhibitor, this is inhibitor. The inhibitor has bound to some other site other than the active site. This is the active site. This is the active site where the substrate is binding. And inhibitor, this is the uncompetitive inhibitor. Uncompetitive inhibitor is binding to the enzyme substrate complex and the sites other than the active site. So this is the site other than the active site. So now you see that in this case, so if this is the reaction, so this is the equilibrium constant is called K dash. Okay, the equilibrium constant will be called K dash. Okay, the equilibrium constant will be called K 1 dash or K dash or K1 dash, whatever. It was called K1 in the case of competitive, here it is called K1 dash. It doesn't matter. So in case of competitive, the equilibrium constant was called K1. Now here we are calling it K1 dash. So now if you draw Michaelis-Menten equation for this, the Michaelis-Menten equation for this kind of equation will become Michaelis-Menten equation will be changed a little bit. Michaelis-Menten equation will be changed for this. The Michaelis-Menten equation is V naught is equal to V max into S by Km plus alpha dash S. Km plus alpha dash S. So what is alpha dash? That time you saw alpha. Here it is alpha dash. And what is alpha dash? Alpha dash is equal to 1 plus I, concentration of I, by Ki dash. This is the equilibrium constant Ki dash. Okay, so 1 plus I by Ki dash. And what is Ki dash? If you are asked what is Ki dash, then you can write K1 dash. This is K1 or Ki. I guess this is Ki instead of K1, or this is for inhibitor. Ki dash is equal to this Ki, not K1, this is Ki, sorry. Ki for K equilibrium constant in presence of uncompetitive inhibitor. And Ki dash is equal to enzyme concentration into substrate concentration divided by enzyme substrate inhibitor concentration. This is how. So one more time I will tell you and then to draw the graph. So let us write down. Actually, in presence of uncompetitive inhibitor, the new Michaelis equation will be transformed in the form of this. That is V naught is equal to V max into S divided by Km plus alpha dash S. Okay. Now, if you are asked what is alpha dash is equal to 1 plus I by Ki dash. Okay. This is equilibrium constant. Okay, this is inhibitor concentration. And what is Ki dash? Then you will write enzyme concentration into substrate concentration, enzyme concentration into substrate concentration divided by enzyme substrate inhibitor concentration. This will give you the enzyme concentration plus enzyme substrate concentration. Sorry, this is not enzyme substrate. You have to say enzyme substrate concentration. Sorry, instead of enzyme and substrate, you have to write what? Enzyme substrate concentration into inhibitor concentration divided by enzyme substrate inhibitor concentration. Because the equation was like this. You see, enzyme plus substrate gives enzyme substrate complex. And then this was enzyme product. Here inhibitor was binding here. So enzyme substrate concentration plus inhibitor concentration gives you what? Enzyme substrate inhibitor concentration. So you have to write like the enzyme substrate concentration into inhibitor concentration divided by enzyme substrate inhibitor concentration, like this. So it was a mistake on my part that I was writing here enzyme substrate concentration, substrate concentration. Normally we write enzyme concentration, substrate concentration divided by enzyme substrate concentration. But in this case, here instead of enzyme you write enzyme substrate concentration because enzyme is binding to the enzyme substrate. Instead of substrate, here you will write inhibitor because inhibitor is binding to enzyme substrate complex. And instead of enzyme substrate concentration, you will write enzyme substrate inhibitor concentration. So if you follow this equation, if you understand this equation, then you can know how I brought the equilibrium constant Ki dash value. Enzyme substrate concentration into inhibitor concentration divided by enzyme substrate inhibitor concentration. So this was a little bit rectification I did. So instead of writing enzyme concentration into substrate concentration divided by enzyme substrate concentration, you have to write enzyme substrate concentration into inhibitor concentration divided by enzyme substrate inhibitor concentration. Okay. Now, since this is the equation, now you do double reciprocal plot. So how will you draw the double reciprocal plot? You see, so you have a say 1 by V naught. You do reciprocal of this, so invert this also. Km plus alpha dash divided by V max into S. Now you separate all the parts. How will you separate it? 1 by V naught is equal to Km divided by V max into S plus alpha dash into S by plus V max. This one will be okay. Yes, alpha dash into S divided by V max into S. You see here, what is the equation? 1 by V naught is equal to Km by V max, Km by V max, okay, into, you can write like this, into 1 by S, right? Km by V max into 1 by S plus S is cancelled out, alpha dash by V max. Okay, very good. So this is the equation. Y is equal to mx plus theta. This is y. This is m, slope. M called slope. M is slope. This is x, and this is intercept of y-axis c. Okay, Vmax. Now you draw the graph. So if you know this one, now I will draw a graph for you. Very easy. So suppose this is the line Weaver Burke plot. This is the line Weaver Burke plot. So without enzyme, say this is without enzyme. Okay, say this is the graph without enzyme. In presence of, this is without enzyme, without any inhibitor. Sorry, without inhibitor. So without inhibitor, this is the graph. So at that time, the value of intercept on x-axis was minus 1 by Km. Do you remember? And intercept on y-axis was 1 by Vmax. Do you remember? 1 by Vmax. This was intercept on y-axis, this was intercept on x-axis. Okay. But now, after the coming of the inhibitor, you will see, after the coming of the inhibitor, this is the parallel line actually. This is a parallel line, so you could draw a parallel line. Okay. After the coming of inhibitor, you see clearly the value of slope Km by Vmax. Okay, the slope has not changed because you have read in mathematics also corresponding angles are equal. When the two lines are parallel, corresponding. This is in the presence of inhibitor. In the presence of inhibitor. What kind of inhibitor? Uncompetitive inhibitor. So the slope does not change. This angle and this angle does not change. The slope is same. But what has happened? You see, instead of K1 minus 1 by Km, the intercept value has become minus alpha by Km. That means the value of Km has reduced a little bit. It is going away from the origin. You see, this is the origin. It is going away from the origin. So the intercept value has become minus alpha dash by Km. The Km value has reduced basically. Similarly, you see here the intercept on axis was 1 by Vmax, but this time the value has decreased by the value has decreased. And what is the decreased value? You know, same. You will write this time the intercept has become alpha dash by Vmax. So this is 1 by substrate concentration, and this is 1 by V naught. So if this value has increased, so 1 by V naught is equal to this one. So V naught will be decreased. Okay, V naught will be decreased. So normally people think that we are increasing. No, this is 1 by V naught. So remember, the value will become lesser. Similarly, people think we are going this side, so the value will increase. How it will increase? This is the origin, and it is in negative. So as you go further, the value is decreasing. You should know, understand this. And this is also 1 by V naught, not V naught. So of course this value is decreasing, not increasing. That means in case of so we come to a conclusion that in case of uncompetitive inhibition, in case of uncompetitive inhibition, in the line Weaver Burke plot, this is called double reciprocal plot or line Weaver Burke plot, what you see, the Km value is also decreasing. Km decreases. Okay, Michaelis constant decreases, and also the Vmax has decreased. Vmax decreases. Okay, Km value has also decreased. Km will be decreased by Km by alpha. The new Km will become Km by alpha dash, and new Vmax, so new Km will become Km by alpha dash times, and Vmax will also decrease. Instead of Vmax, now you will write Vmax by alpha dash. Means both the value of Km and the Vmax is decreasing. So you have to understand this point, that this is not increase, this is decrease. Why this is decrease? Because this is 1 by V naught. Similarly, when you go farther from origin, this is not increasing, this is decreasing. You have to understand this. Okay, this is origin, you are going beyond origin. So this is called. So we have learned that Km decreases in case of uncompetitive inhibition. Km decreases and Vmax also decreases. The new Km will become Km by alpha dash, decreased value, and Vmax will decrease, become Vmax by alpha dash. So now we have already done with uncompetitive inhibition. Uncompetitive inhibition. Now let us come to another point, is called mixed. Now we are coming to mixed inhibitor or mixed inhibition. In mixed inhibition also Km and Vmax are changed, but in special case, if we talk about mixed inhibition, okay, in case of mixed inhibition, if you see mixed inhibition, then V naught, the Michaelis-Menten equation become V naught is equal to Vmax into S divided by alpha Km plus alpha dash S. You see why I have written this equation? Because in case of mixed inhibition or special case, in special case of mixed inhibition is called non-competitive inhibition. Non-competitive inhibition. When alpha becomes equal to alpha dash become equal to alpha. When alpha and alpha dash become equal, then in that case mixed inhibition is called non-competitive inhibition. Remember, mixed inhibition, a special case of mixed inhibition is called non-competitive inhibition when alpha is become equal to alpha dash. So now you must be wondering, like you see enzyme plus substrate gives enzyme substrate complex, and then you get enzyme and the product. In mixed inhibitors, what is the beauty of mixed inhibitor? That they can bind to the enzyme also. They can bind to the enzyme also and becomes enzyme inhibitor complex, and they can bind to the substrate also. Okay, and form enzyme substrate inhibitor complex. So this is the difference between uncompetitive and mixed inhibitor. So in mixed inhibitor, what you see that they also bind to the site different from active site. Okay, do you understand what I am saying? But they can bind to the enzyme as well as they are free to bind to the enzyme substrate complex. So this is very important when you are trying to understand. Then you have to know that they can bind to the enzyme also and they can bind to the enzyme substrate complexes. So like in the figure I tried to explain you. Suppose this is the enzyme, okay, and this is the enzyme, okay. Then they can bind to the inhibitor can bind to the enzyme also, and it is also possible that suppose this is the okay. Let me write like this. They also bind to the site other than active site, but they are free to bind either to the enzyme or to the enzyme substrate complex. Only this much I think will suffice. If it is not, then I can draw the picture for you, but it will take a lot of time to draw the picture. So just to understand that inhibitors, mixed inhibitors are also binding to the enzyme or to the enzyme substrate complex, but they will bind to the site other than active site where substrate bind. They will not bind to the place where substrate bind. They will bind. They will, like uncompetitive inhibitors, they will also bind to some other place, not at the active site, but they can bind either to the free enzyme or to the enzyme substrate complex. Okay. Now you see, in a special case, now how will you define alpha? You already know what is alpha. I don't have to tell you. Alpha is equal to 1 plus I by Km, right? And alpha dash is equal to what? 1 plus I dash. Alpha is equal to what? Alpha is equal to what is alpha? Alpha is equal to 1 plus I by Ki, right? And alpha dash is equal to 1 plus I by Ki. Okay, here I by Ki dash. Okay, do you understand? Why? Because your equation is something like that. Enzyme plus substrate gives enzyme substrate complex, and then you get enzyme plus product. Your substrate can bind here also, right? So this one will be, this will form enzyme. Your inhibitor can bind here also, so it will form enzyme inhibitor complex. And here the value becomes Ki, just Ki. But when inhibitor is binding here, then it will form, and then it will form what? Enzyme substrate inhibitor complex. And in this case, the equilibrium constant name will be Ki dash. So if only Ki, the value, the Ki, okay, Ki. So how will you define Ki? Ki is equal to, you already know, enzyme plus inhibitor divided by enzyme inhibitor complex. And how will you define Ki dash? So how will you define Ki dash? Tell me. Ki dash will be defined as enzyme substrate complex into inhibitor complex divided by enzyme substrate inhibitor. So if you know the value of enzyme substrate concentration, inhibitor concentration, enzyme substrate inhibitor, you can find Ki dash, and from Ki dash you can find alpha dash. Similarly, if you know inhibitor concentration, Ki equilibrium constant in presence of inhibitor, you can find the value of alpha. So now, since alpha, now you see, now let us do the reciprocal plot of this equation. So reciprocal, how will you do reciprocal? So let us do the reciprocal. In a hurry, we should do it. So this is 1 by V naught. This is alpha Km by V max into S. And similarly here, just do reciprocal. So alpha dash into S divided by V max into S. I have already reciprocated it and have separated it. Okay. So this SS cancels out. So 1 by V naught is equal to alpha Km by V max into 1 by S, right? Plus alpha dash by V max. Since alpha is equal to alpha dash, so instead of alpha dash we can write alpha. So 1 by V naught is equal to alpha Km by V max into V max, okay, into 1 by S, right? Plus this also we can write alpha by V max. Clearly you see that here, what do you see? What do you see here? Can you tell me from this equation? What do you see from this equation? This is y, this is become n, new n, this is slope, this is 1 by s, this is x, and this is the intercept from y-axis. Let us draw a graph. So this is slope, okay, slope. So now you have this equation. Draw a graph. Please draw a graph. So how will you draw a graph for this? It's easy. You see? Okay. So without inhibitor, let us say the graph is like this. This is without inhibitor. You know this side is 1 by s and this side is this y-axis is 1 by v naught. Okay. Now in presence of inhibitor, you see the slope has changed alpha time. This is m. Alpha is normally the slope is km by Vmax. Now the slope has become alpha km by Vmax. So slope is little bit increased, right? But you see, but the value of, so you see, intercept normally. Okay, so I will draw like this. Can you see here? Initially the slope was this much, km by Vmax. But in presence of, in case of non-competitive inhibition, in case of non-competitive inhibitor, okay, no inhibitor, non-competitive inhibitor. You see, the angle has increased now. The slope is increasing. The slope has increased. The slope has increased. Okay? But, and the Vmax, you see, this was 1 by Vmax. Do you remember? Without inhibitor. But this time also, what has it been? The new intercept on y-axis, how will it become? It will become alpha by Vmax. That means the Vmax is decreasing, but the Km does not change. You see, what is the normal value of Km? Minus 1 by Km. The Km has not changed, not decreasing. Km remains the same place. Without inhibitor also start from the same place, and in the presence of inhibitor also start from the same place. So the value of Km is not changing. Clearly, the value of Km is not changing, but the slope has changed and intercept on y-axis has changed. So Vmax is decreased. Vmax is decreased. Do you understand? Alpha by Vmax. So Vmax has changed. Vmax has changed. So since alpha by, it has become alpha by Vmax. So 1 by V naught is equal to this much. So V naught is of course decreased. You see, it is not just V naught, it is 1 by V naught. So the value has, the total value of Vmax has decreased. So in case of, we can say, in case of non-competitive inhibition, non-competitive is a special type of mixed inhibition. Number 1, Km remains unchanged. See, Km has not increased or decreased. Okay, Km remains unchanged. But the Vmax has decreased. Vmax. Many students of biology, they think that this is increasing. No, because this is 1 by V naught, you see. So the value of Vmax is decreasing, not increasing. Remember, so Vmax decreases and Km does not change. So we can write like this. We see in mixed inhibitor, Vmax and Km both changes. But since here alpha and alpha dash is same, so that's why Km is not. Actually, the Km should have changed. You see, I will explain you like this. Let me explain you like this. In mixed, the Vmax, actually Vmax should become Vmax by alpha. Vmax should become Vmax by alpha dash. Vmax by alpha dash means it should decrease by alpha, and Km should also increase or decrease depends. So it should have been actually alpha Km by alpha dash. Alpha Km by alpha dash. So the Vmax also changes and Km also changes. But this is a special case where alpha and alpha dash are same. So alpha and alpha dash are same. So Km does not change. Instead, Km remains the same. So the new Km remains the same. Actually, the Km should have changed as the Vmax is changing. But since alpha and alpha dash are same, that's why the Km does not change. Remember, it's a special case when alpha dash and alpha becomes equal. When alpha dash and alpha becomes equal, so the value of Km will not change. That's why this is going in this way. So what have you learned here? We have learned here that in case of mixed inhibition, a special case of mixed inhibition called competitive inhibition, non-competitive inhibition, the Km value does not decrease, but the value of Vmax has decreased. Okay, so now we have already done with non-competitive inhibition. Now, one last I want to tell you that we have already learned that reversible inhibitions are of three types. What are they? Competitive, uncompetitive, and non-competitive. We have learned the graphs of all of them. We have learned the graph how to draw double reciprocal plot for all of them. Okay, we have learned two. So I will just summarize it. In case of this is say competitive. Okay, this is uncompetitive, and this is non-competitive inhibition. Just see and you will understand. So here we have a graph, here we have a graph, here we have a graph. So in this case, this is normal, okay, without inhibitor. In presence of inhibitor, how will it look? In presence of inhibitor, we have already discussed. In presence of inhibitor, what will happen? Like this. In presence of inhibitor, Km is increasing, Vmax unchanged. Okay? In this case, in uncompetitive, what did you see? Without inhibitor is like this. With inhibitor is parallel. You already know this. Just now I have told you. And in case of non-competitive, without inhibitor is like this. In presence of inhibitor is like this. So here you can clearly see Km increases, Vmax unchanged. Okay, this is 1 by S, this is 1 by V naught, this is 1 by S, this is 1 by V naught, this is 1 by S, and this is 1 by V naught. Okay, so this is without and with. This color is without inhibitor. Okay, and this one is with inhibitor, competitive inhibitor. So similar you can understand for all. Okay, so here you see Km increases, Km was this, it has increased, it has come more near to G origin. So this Km has increased, Vmax is unchanged. Here you see Km also decreasing, Vmax also decreasing. Km decreases and Vmax also decreases. And in case of non-competitive, you see Km unchanged, no change in Km. For this orange color and blue color graph, you see Km, but Vmax has decreased. So this, if you remember, then all problems will be solved. Okay. Now we have already learned these were reversible inhibition. These all three cases was in the case of reversible. Now I will just discuss for 2 minutes or 3 minutes hardly what is non-reversible inhibition. It is very easy. Non-reversible inhibition. Here there will be no reverse. Non-reversible inhibition is an inhibition. Irreversible you can say. Irreversible you can say. Instead of non-reversible, you can say irreversible inhibition. Here, what happens that since it is irreversible, it will not be able to reverse, and the inhibitors bind covalently with or destroy functional group on an enzyme. So, covalent bond will be formed between the enzyme and the inhibitor. So the functional group of the enzyme will be destroyed, or it is quite possible they will form non-covalent association, but that is very stable. For example, I will tell you how, if covalent bond is formed between the functional groups of an enzyme with some inhibitor, irreversible inhibitor. One irreversible inhibitor I will show you. Suppose this is enzyme, and enzyme has a CH2OH group of serine. Serine has a CH2OH functional group is you know the functional group here present is here OH, CH2OH actually. So this is the enzyme. And from another side, one inhibitor is coming. The name of the inhibitor is DIFP, diisopropyl fluorophosphate. So this is the inhibitor name is diisopropyl fluorophosphate. So what is isopropyl? CH3. This is isopropyl and diisopropyl CH. So this is isopropyl group. Isopropyl group CH3 CH3 is called isopropyl group. Diisopropyl fluorophosphate. So you just one fluorine here. So this will become diisopropyl. See, this is isopropyl, this is isopropyl. So name becomes diisopropyl fluorophosphate. Fluorophosphate. DIFP. Diisopropyl. Diisopropyl fluorophosphate. This is the irreversible inhibitor. How it will react with this and form a covalent bond. It will react with it and form a covalent bond. Okay. So the fluorine will be removed. The fluorine will be removed. You see, when these two are reacting, what will happen? You will just see. This will become enzyme. This is CH2. This is O, and fluorine will be removed, and it will form permanent covalent bond. You see, CH3, okay, CH3, and here it will become O, CH3. What do you see? A permanent bond is formed between the enzyme functional group and the inhibitor. Covalent bond is formed. So this has become permanently blocked. Permanently covalently binding with the enzyme with a covalent bond, and so it is inhibiting permanently a kind of irreversible inhibitor. So DIFP is an irreversible inhibitor in which the functional group links with the irreversible inhibitor by a covalent bond. Irreversible inhibitors are another useful tool for studying reaction mechanism. So if you want to understand the reaction mechanism well, then you have to also understand what is irreversible inhibitor. And if you cannot understand irreversible inhibitor in this way, I will tell you the very common example of irreversible inhibitor. Most of them are toxic substance, and the antibiotic, you know, whenever you are having some problem, you take some antibiotic, say penicillin. So what is penicillin doing actually? The antibiotic penicillin act as an irreversible inhibitor of enzyme glycopeptide transpeptidase. Penicillin is a irreversible inhibitor. Irreversible inhibitor. For which enzyme? The name of the enzyme is what? Glycopeptide transpeptidase. Glycopeptide transpeptidase. Do you remember this enzyme? Glycopeptide transpeptidase. When you were studying the cell wall composition of bacteria, in that you see that how cross-linking of the peptidoglycan chain during the synthesis of bacterial cell wall takes place. Cross-linking of the peptide chain in the cell wall of bacteria took place with the help of enzyme glycopeptide transpeptidase. Now, if penicillin is going and irreversibly binding, covalently binding, goes and binds to this enzyme, what will happen? Cross-linking will not be possible, and if the cross-linking is not possible, then cell wall will not be formed properly. And if the bacterial cell wall is not synthesis is blocked, then what will happen? It will go osmotic lysis and the bacteria will die. That's why when you take penicillin, the bacteria dies because of the osmotic lysis, the bacteria, and thus bacterial growth is stopped. So you have learned the two examples of irreversible inhibitors. What is irreversible inhibitor? For example, DIFP, diisopropyl fluorophosphate, how it binds covalently with the OH group of the serine and inhibits the enzyme. Similarly, what is the name of the enzyme? DIFP is blocking. The name of the enzyme the DIFP is blocking is the chymotrypsin, reaction of chymotrypsin. This is chymotrypsin. What is the name of this enzyme? Chymotrypsin. So you know the function of chymotrypsin. The students of zoology must be knowing what is the function of chymotrypsin. This chymotrypsin has a serine functional group, and this diisopropyl fluorophosphate reacts covalently with this OH residue and blocks the enzyme. Similarly, in case of penicillin, penicillin acting as an irreversible inhibitor for the enzyme lipopeptide transpeptidase, and thus the cross-linking of the cross-linking does not take place while in the synthesis of the cell of bacteria, and that in this way the bacteria dies because of osmotic lysis, because the cross-linking of the peptide chains are blocked during the formation of cell-wall in bacteria. So, I hope you understood what is reversible and what is irreversible inhibition. In reversible inhibition, you have learned there are three types. They are competitive, uncompetitive, and non-competitive. You learned how to draw the reciprocal plot and how to understand it, the things. And in case of irreversible inhibition, you have learned about how penicillin acts as an irreversible inhibitor for enzyme lipopeptide transpeptidase, and how DIFP, diisopropyl fluorophosphate, is acting as an inhibitor for the enzyme chymotrypsin by binding covalently to the serine residues or other residues present on the functional group present on the enzyme. Thank you so much.